going to try and find the constant in our density function, rho naught. So we say that the charge within a small volume dV is dq equals rho times dV. This makes sense. Rho is charge density, dV is a volume, so we multiply the density times the volume and we get the charge. The integral of rho dV over a cylinder gives us the total charge, and that total charge could also be written as lambda times L. So let's put these things together and find the value for our constant rho naught. So let's start with those two things. Q equals lambda times L. So there's the first thing we know. We also know that Q is equal to the addition of all the small amounts of charge on the cylinder, which is the density times the volume. Okay, there we go. So this part just comes from the fact that if we want the total charge on this cylinder, we have to add up all of the bits of charge. So let's do a little bit more with this right here. How do we put this together? And then eventually we'll sub in our lambda L for Q and we'll sort this out. So rho is not going to be too difficult to deal with. Rho is r times rho naught divided by the radius of the cylinder, and r is your radial coordinate, your distance from the center. But what about dV? What does that mean? It doesn't really say what dV is here. So let's look at our cylinder. I'll try and draw something big enough so that we can have a look at it. So here's a cylinder. It's got length L. It's got the radius r. And we're saying that we'd get the total charge on this cylinder if we added up all of the pieces of the charge and we got them all together. So what do we mean by a piece of charge? Well, if we want to find the area of a cylinder, or if we want to find the volume of a cylinder, what we could do is consider little cylindrical shells. So if we got a shell of the cylinder, and if that shell had radius r, if we added up a shell from the center, and why don't we try and make that 3D? It's a little bit hard to draw, but I'll give it a shot. Okay, so there's a 3D cylindrical shell with radius r. And in fact, why don't we even draw a face-on version? So a facing view. So there's the edge view. And our shell, our piece of our volume, which has a piece of charge, would look like a circle when we're edge on, so that would have radius r. Let's get another label on here. It has a radius of r, so it has a thickness, which is in the radial direction, of dr. So thickness equals dr. So dV equals a thin shell. The thin shell has a radius of r, and it has a thickness, dr. And it carries charge dq. Okay, now we've put some stuff together. We have an idea of what we're looking at here. So to get our total amount of charge, we're going to have to add it all up. So we need a usable expression for our dV. How are we going to write down what dV is so that we can plug it in here and we can do our integral? So if dV is the volume of the shell, the next question we'd ask is, how do we find the volume of the shell? Well, we could find the volume by multiplying the area of the shell by its length. So a volume is area times length, so we could put that in there. So now let's ask, what is the area of the shell? Well, let's take our shell. We know that an area can be length times width. What does that mean in the terms of a cylinder? Well, the width part is easy. The width is dr, that's the thickness. So dr is okay. That's the width of this cylindrical shell right here. The length is the distance all the way around. So that length would be the circumference. So that's how we can find an expression for the volume element of our shell. So dV is the little bit of volume of this thin shell. It has radius r, thickness dr, it carries charge dq, which is given by density times the volume. The volume would be the area of the shell times the length of the shell. And the area would be 2 pi r times dr, so the length times the thickness, and then we multiply that by the length of the whole thing to get the volume of the shell. 2 pi r dr. So now we have somewhere to go with this. Q is the integral of rho times dV. For rho, we'll put in the given expression, so that guy is given. For dV, we'll put in what we just figured out, and then we'll figure out what our total charge is, and then we'll put that together with this expression and find our constant rho naught. So let's start right at the beginning. Q, the net charge, is the integral of rho times dV. Let's put in the two things that we know. So our value of rho is r times our constant divided by the radius of the cylinder. And dV is the volume of our cylindrical shell, which is the area times the length. So we said that that volume was 2 pi r dr. Now we have an expression for the net charge on that cylinder. So let's get to work on solving this guy. Oh, and I dropped my length. 2 pi r times dr times the length. The first thing we can do with our integral is take the constants out front. So what do we have in this integral that's constant? Rho naught is constant, 2 pi is constant, L is constant, radius of the cylinder is constant, so all those guys are out front. We're left with the integral of r times r, that's r squared, times dr. So this is a good time to sort out the limits. What are the limits of this integral? So we're adding up every single shell. We'll start at the middle and we'll go out to the edge. So our initial limit, our lower limit is 0. Our upper limit is the radius of the cylinder, r. So our integral goes from 0 to uppercase r. So now we can evaluate our integral. The integral of r squared is r cubed over 3. That's evaluated at r and 0. So we have rho naught times 2 pi L over r times r cubed over 3 minus 0 cubed over 3 equals rho naught times 2 times pi times L times r cubed over 3 times r. So there's our expression for the net charge. Let's just rewrite it and neaten it up a little bit. So Q is equal to 2/3 times pi times rho naught times L times r squared. There's an expression for the net charge on the cylinder. The other expression we have for the net charge on the cylinder is that the net charge is the charge density times the length. Let's put these two together. See that our L's cancel and we can solve for rho naught. Rho naught is equal to 3 times lambda over 2 times pi times r squared. There's the expression for the constant in our density function, and we can fill that in next if we wish. So density as a function of radial position is equal to the radial position times rho naught r squared divided by r, so that'll give us r cubed on the bottom. So there's our expression for density. Okay, next we'll move on to the last part, which is define the electric field inside the cylinder.